Hello, my name is Samantha Deans, and welcome to Lab 1, Constant Velocity. The purpose of this lab is to compare the observed position versus time to the predicted position versus time of an object moving at a constant velocity. The object used for the experiment will be an empty cylindrical bottle. The tracker program will be used to calculate the values for observed position versus time, and GlowScript will create the computational model used to calculate the predicted values for position versus time. This lab is meant to demonstrate Newton's second law. So Newton's second law tells us that the net force is equal to the change in momentum divided by the change in time. So if we take that initial equation up at the top and we derive it further, we get that the final velocity is equal to the initial velocity plus net force divided by mass times change in time. So this tells us that if net force is 0, that final velocity is equal to initial velocity. Now here's the video of our circular object rolling across the floor at a constant velocity. By selecting the center of mass using these diamond icons for each frame of the video, we get the graph and the data points for our observed value of position based on time. So from that video that we took of our circular object rolling, we can get our first two data points. From this, we can find our initial position, in which the vector is negative 0.0114 meters in the negative x direction, meaning it's going towards the left. And from this, we can find our initial velocity, which is equal to negative 13.073 meters per second in the x direction, meaning it is going to the left. So now that we have our initial conditions from the previous slide, we can start to set up our computational model to find our expected position versus time values. So first I set the net force to 0 since constant velocity means no net force. Then I input the initial velocity and position that we had previously obtained from our tracker analysis. Next, I set delta t to 1/30 since the video we recorded at 30 frames per second. And then next, the mass of the ball does not affect velocity whatsoever since the velocity update formula says that if net force is 0, that mass just cancels out. And so now for the position formula, we are going to use to predict the location. And since our velocity is constant, we should see a negative slope because our object is going from right to left. So now that we've obtained all of our observed versus predicted data, we can create this graph where we see a trend with the observed data that the observed position does not make it as far as the predicted position, meaning that there has to be some external force at play. So some possible sources of error include both external forces and human error in tracking position. But first, let's define the system and the surrounding in this experiment. So the system in this case is the cylindrical bottle rolling on the floor. And our surrounding is everything else on Earth, in outer space, everything. So in this case, external forces could include friction from the bottle rolling across the ground and air resistance, as air molecules are pushing on this and resisting it from where it wants to go. Next, we have human error in tracking position. This is probably a smaller one, but as I was deciding the center of mass for each frame, it may not have been 100% precise since I was doing it by hand. So that's another possible source of error. Finally, for some additional questions, for question 1, if positive x and negative x were interchanged, the only thing that would happen here is that the slope would go from negative to positive. All the other physics and everything else calculated would be the exact same. And next, is the net force 0? So since our object slowed down and didn't go as far as it was expected, there had to have been forces involved. So in terms of the y direction, the net force was 0. Otherwise, it would go flying into outer space or into the center of the Earth. So gravity and the normal force cancel each other out to create a net force of 0 in the y. However, in the x, some force, for example, friction, must have been at play to slow our object down.